Assalamualaikum everyone, welcome to College Physics. Today we're going to be going through the scheme of work for Cambridge International AS and A-Level Physics 9702. What we will be basically discussing is for example, we have physics, right? We'll be discussing the key concepts, which are the main topics, and then the subtopics, which we'll be learning through learning objectives. The topics that we will be discussing will be physical quantities and units, kinematics, dynamics, forces, work, energy and power, density and pressure, deformation of solids, waves, superposition, electricity, DC circuit, particle physics and nuclear physics, motion in a circle, gravitational fields, temperature, ideal gases and thermodynamics, oscillations, electric fields, capacitance, magnetic fields and alternating currents, quantum physics, medical physics, astronomy, and cosmology. Up first, we have physical quantities and units. The key concepts: 1.1, physical quantities, 1.2, SI units. The learning objectives: 1.1.1, understand that all physical quantities consist of numerical magnitude and a unit. 1.1.2, make reasonable estimates of physical quantities included within the syllabus. 1.2.1, recall the following SI-based quantities and their units. For example, mass, kg, length, meter, time, seconds, current, ampere, temperature, Kelvin. Express derived units as products or quotients of the SI-based units and use the derived units for quantities listed in the syllabus as appropriate. 1.2.3, use SI-based units to check the homogeneity of physical equations. 1.2.4, recall and use prefixes and their symbols to indicate decimal, submultitudes, or multiples of both base and derived units. Then we have another key concept, which is errors and uncertainties. The learning objectives in this is 1.3.1, understand and explain the effects of systematic errors, including zero error, and random errors in measurements. 1.3.2, understand the distinction between precision and accuracy. 1.3.3, assess the uncertainty in a derived quantity by simple addition of absolute or percentage uncertainties. Next key concept we have 1.4, scalars and vectors. The learning objectives: understand the difference between scalar and vector quantities and give examples of scalar and vector quantities included in the syllabus. 1.4.2, add and subtract coplanar vectors. 1.4.3, represent a vector as two perpendicular components. Next we have kinematics. The key concepts: 2.1, equations of motion. The learning objectives: 2.1.1, define and use distance, displacement, speed, velocity, and acceleration. 2.1.2, use graphical methods to represent distance, displacement, speed, velocity, and acceleration. 2.1.3, determine displacement from the area under the velocity time graph. 2.1.4, determine velocity using a gradient of displacement time graph. 2.1.5, determine acceleration using the gradient of a velocity time graph. The next key concept, 2.1, equations of motion. The learning objectives: 2.1.6, derive from the definitions of velocity and acceleration equations that represent uniform acceleration motion in a straight line. 2.1.7, solve problems using equations that represent uniformly accelerated motion in a straight line, including the motion of bodies falling in a uniform gravitational field without air resistance. The next key concept, equations of motion. The learning objectives: 2.1.8, describe an experiment to determine the acceleration of free fall using a falling object. The next key concept, 2.1, equations of motion. 2.1.9, the learning objectives, describe and explain motion due to a uniform velocity in one direction and uniform acceleration in a perpendicular direction. Dynamics. The key concept: 3.1, momentum and Newton's law of motion. The learning objectives: 3.1.1 Understand that mass is the property of an object that resists in motion. 3.1.2 Recall force is equal to mass into acceleration and solve it. Using it, understand that acceleration and resultant force are always in the same direction. 3.1.3 Define and use linear momentum as the product of mass and velocity. 3.1.4 Define and use force as rate of change of momentum. 3.1.5 State and apply each of Newton's laws of motion. 3.1.6 Describe and use the concept of weight as the effect of a gravitational field on a mass, and recall that the weight of a body is equal to the product of its mass and the acceleration of its free fall. In other words, W is equals to mg. The next key concept, 3.2, non-uniform motion. The learning objectives. 3.2.1, show a quantitative understanding of frictional forces and viscous/drag forces, including air resistance. 3.2.2, describe and explain quantitatively the motion of objects in a uniform gravitational field with air resistance. 3.2.3, understand that objects moving against a resistive force may reach a terminal, which is the constant velocity. Another key concept, 3.3, linear momentum and its conservation. Learning objectives. 3.3.1, state the principle of conservation of momentum. 3.3.2, apply the principle of conservation of momentum to solve simple problems, including elastic and inelastic interactions between objects in both 1 and 2 dimensions. 3.3.3, recall that for a perfectly elastic collision, the relative speed of approach is equal to the relative speed of separation. 3.3.4, understand that while momentum of a system is always conserved in interactions between objects, some change in kinetic energy may take place. Next we have forces. The key concept. 4.1, turning effects of forces. The learning objectives. 4.1.1, understand that weight of a body may be taken as acting at a single point known as its center of gravity. 4.1.2, define and apply the moment of a force. 4.1.3, understand that a couple is a pair of forces that act to produce rotation only. 4.1.4, define and apply the torque of a couple. The next key concept. 4.2, equilibrium of forces. The learning objectives. 4.2.1, state and apply the principle of moments. 4.2.2, understand that when there is no resultant force and no resultant torque, a system is in equilibrium. 4.2.3, use a vector triangle to represent coplanar forces in equilibrium. Work, energy, power. The key concepts, gravitational potential energy and kinetic energy. Learning objectives. 5.1.1, understand the concept of work and recall and use. Work done is equals to force into displacement in the direction of the force. 5.2.1, derive using formula. Work is equals to force into distance. The formula, gravitational potential energy is equals to mgh for gravitational potential energy in a uniform gravitational field. 5.2.2, recall and use the formula. E is equals to mgh for gravitational potential energy changes in a uniform gravitational field. 5.2.3, derive using the equations of motion the formula for kinetic energy. E is equals to half mv squared. 5.2.4, recall and use E is equals to half mv squared. Key concept. 5.1, energy conservation. The learning objectives. 5.1.2, recall and apply the principles of conservation of energy. 5.1.3, recall and understand that the efficiency of a system is the ratio of useful energy output from the system to the total energy input. 5.1.4, use the concept of efficiency to solve problem. Another key concept. 5.1, energy conservation. The learning objectives. 5.1.5, define power as work done per unit time. 5.1.6, solve problems using power is equals to work done upon time. 5.1.7, derive power is equals to force into velocity and use it to solve problems. 6. Density, pressure, and deformation of solids. Key concepts. 4.3 Density and Pressure. The learning objectives. 4.3.1 Derive and use density. 4.3.2 Derive and use pressure. 4.3.3 Derive from the definitions of pressure and density the equation for hydrostatic pressure. P is equals to rho gh. 4.3.4 Use the equation P is equals to rho gh. 4.3.5 Understand that the upthrust acting on an object in a fluid is due to a difference in hydrostatic pressure. 4.3.6 Calculating the upthrust acting on an object in a fluid using the equation F is equals to rho gv, the Archimedes principle. Key concept 6.1 Stress and strain. 6.2 Elastic and plastic behavior. The learning objectives. 6.1.1 Understand that deformation is caused by tensile or compressive forces. 6.1.2 Understand and use the terms load, extension, compression, and limit of proportionality. 6.1.3 Recall and use Hooke's law. 6.1.4 Recall and use the formula for Spring's constant. Spring's constant, or K, is equals to force upon X, which is extension. 6.2.1 Understand and use the terms elastic deformation, plastic deformation, and elastic limit. 6.2.2 Understand that the area under the force extension graph represents the work done. 6.2.3 Determine the elastic potential energy of a material deformed within its limit of proportionality from the area under the force extension graph. 6.2.4 Recall and use E is equals to half Fx is equals to half kx squared for a material deformed within its limit of proportionality. Key concept 6.1 Stress and strain. The learning objectives. 6.1.5 Define and use the term stress, strain, and the Young modulus. 6.1.6 Describe an experiment to determine the Young modulus of a metal in the form of a wire. Waves and superposition. Key concepts. Progressive waves. The learning objectives. 7.1.1 Describe what is meant by wave motion as illustrated by vibration in ropes, springs, and ripple tanks. 7.1.2 Understand and use the terms displacement, amplitude, phase difference, period, frequency, wavelength, and speed. 7.1.3 Understand the use of time base and Y gain of a cathode ray oscilloscope, or CRO, to determine frequency and amplitude. 7.1.4 Determine using the definitions of speed, frequency, and wavelength the wave equation V is equals to F lambda. 7.1.5 Recall and use V is equals to F lambda. 7.1.6 7.1.7 Recall and use intensity is equals to power upon area, and intensity is directly proportional to amplitude squared for progressive wave. Key concept 7.2 Transverse and longitudinal wave. Learning objectives. 7.2.1 Compare transverse and longitudinal waves. 7.2.2 Analyze and interpret graphical representations of transverse and longitudinal waves. Key concept 7.3 Doppler effect for sound waves. Learning objectives. 7.3.1 Understand that when a source of sound wave moves relative to a stationary observer, the observed frequency is different from the source frequency. 7.3.2 Use the expression FO is equals to FSV upon V plus minus Vs for the observed frequency when a sound of source moves relative to a stationary observer. Key concept 7.4 Electromagnetic spectrum. The learning objectives. 7.4.1 State that all electromagnetic waves are transverse waves that travel with the same speed c in space-time. Recall the approximate range of wavelengths in free spaces of the principal regions of the electromagnetic spectrum from radio waves to gamma waves. 7.4.3 Recall that wavelengths in the range 400 to 700 nanometers in the free space are visible to the human eye. Key concept 7.5 Polarization, the learning objectives. 7.5.1 Understand the polarization is a phenomena associated with transverse wave. 7.5.2 Recall and use Moluss's law I is equals to I0 cos squared theta to calculate the intensity of a plane polarized electromagnetic wave after transmission through a polarizing filter or a series of polarizing filters. Key concept stationary waves. Learning objectives 8.1.1 Explain and use the principle of superposition. 7.1.2 Show an understanding of experiments that demonstrate stationary waves using microwaves, stretched strings, and air columns. 8.1.3 Explain the formation of a stationary wave using a graphical method and identify nodes and antinodes. 8.1.4 Understand how wavelength may be determined from the positions of nodes and antinodes of a stationary wave. Key concept 8.2 Learning objectives 8.2.1 Explain the meaning of the term diffraction. 8.2.2 Show an understanding of experiments that demonstrate diffraction, including the quantitative effect of the gap width relative to the wavelength of the wave. 8.3 Key concept 8.3 Interference. The learning objectives 8.3.1 Understand the terms interference and coherence. 8.3.2 Show an understanding of experiments that demonstrate two source interference using water waves in a ripple tank, sound, light, and microwaves. 8.3.3 Understand the conditions required if two source interference fringes are to be observed. 8.3.4 Recall and use lambda is equals to ax upon d for double slit interference using light. 8.4 The diffraction grating. 8.4.1 Recall and use d sine theta is equals to n lambda. 8.4.2 Describe the use of a diffraction grating to determine the wavelength of light. Electricity and DC circuits. Key concept 9.1 Electric circuit. Learning objectives 9.1.1 Understand that an electric current is a flow of charge carriers. 9.1.2 Understand that charge on charge carriers is quantized. 9.1.3 Recall and use Q is equals to IT. 9.1.4 Use for a current carrying conductor the expression I is equals to A and VQ, where N is the number density of charge carriers. Key concepts 9.2 Potential difference and power. Learning objectives 9.2.1 Define the potential difference across a component as the energy transferred per unit charge. 9.2.2 Recall and use V is equals to W upon Q. 9.2.3 Recall and use P is equals to IV, P is equals to I squared R, and P is equals to V squared upon R. Key concept 9.3 Resistance and resistivity. Learning objectives 9.3.1 Define resistance. 9.3.2 Recall and use V is equals to IR. 9.3.3 Sketch the IV characteristics of a metallic conductor at constant temperature, a semiconductor diode, and a filament lamp. 9.3.4 Explain that the resistance of a filament lamp increases as current increases because its temperature increases. 9.3.5 States Ohm's law. 9.3.6 Recall and use R is equals to PL upon A. 9.3.7 Understand that the resistance of a light-dependent resistor, an LDR, decreases as the light intensity increases. 9.3.8 Understand that the resistance of a thermistor decreases as the temperature increases. Key concept 10.1 Practical circuits. The learning objectives 10.1.1 Recall and use the circuit symbols shown in the syllabus. 10.1.2 Draw and interpret circuit diagrams. 10.1.3 Define and use electromotive force of a source as energy transferred per unit charge in driving charge around a complete circuit. 10.1.4 Distinguish between EMF and potential difference, PD, in terms of energy considerations. 10.1.5 Understand the effects of an internal resistance of a source of EMF on the terminal potential difference. Key concepts. 10.2 Kirchhoff's Law. Learning objectives. 10.2.1 Recall Kirchhoff's law, first law, and understand that it is a consequence of conservation of energy. 10.2.2 Recall Kirchhoff's law, second law, and understand that it is a consequence of conservation of energy. 10.2.3 Derive, using Kirchhoff's law, a formula for the combined resistance of two or more resistors in series. 10.2.4 Use the formula for combined resistance of two or more resistors in series. 10.2.5 Derive, using Kirchhoff's law, a formula for the combined resistance of two or more resistors in parallel. 10.2.6 Use the formula for the combined resistance of two or more resistors in parallel. 10.2.7 Use Kirchhoff's law to solve simple circuit problems. Key concept. 10.3 Potential dividers. Learning objectives. 10.3.1 Understand the principle of a potential divider circuit. 10.3.2 Recall and use the principle of the potentiometer as a means of comparing potential differences. 10.3.3 Understand the use of a galvanometer in null methods. 10.3.4 Explain the use of thermistors and light-dependent resistors in potential dividers to provide a potential difference that doesn't depend on temperature and light intensity. Motion in a circuit. Key concepts. 12.1 Kinematics of uniform circular motion. Learning objectives. 12.1.1 Define the radian and express angular displacement in radians. 10.1.2 Understand and use the concept of angular speed. 12.1.3 Recall and use W is equals to 2 pi upon T and V is equals to RW. Key concept. 12.2 Centripetal acceleration. Learning objectives. 12.2.1 Understand that a force of constant magnitude that is always perpendicular to the direction of motion causes centripetal acceleration. 12.2.2 Understand that centripetal acceleration causes circular motion with a constant angular speed. 12.2.3 Recall and use A is equals to RW squared and A is equals to V squared upon R. 12.2.4 Recall and use F is equals to MRW squared and F is equals to MV squared upon R. Gravitational fields. Key concept. 13.1 Gravitational fields. Learning objectives. 13.1.1 Understand that a gravitational field is an example of a field of force and define gravitational field as force per unit mass. 13.1.2 Represent a gravitational field by means of field lines. 13.2.1 Understand that for a point outside a uniform sphere, the mass of the sphere may be considered to be a point mass at its center. Key concept. 13.2 Gravitational forces between point masses. Learning objectives. 13.2.2 Recall and use Newton's law of gravitation. F is equals to Gm1 m2 upon r squared for the force between 2 point masses. 13.2.3 Analyze circular orbits in gravitational fields by relating the gravitational force to the centripetal acceleration it causes. 13.2.4 Understand that a satellite in a geostationary orbit remains at the same point above the Earth's surface with an orbital period of 24 hours, orbiting from west to east directly above the equator. Key concept. Gravitational field of a point mass. Learning objectives. 13.3.1 Derived from Newton's law of gravitation and the definition of gravitational field, the equation G is equals to Gm upon r squared for the gravitational field strength due to a point mass. 13.3.2 Recall and use G is equals to Gm upon r squared. 13.3.3 Understand why G is approximately constant for small changes in height near the Earth's surface. Key concept. Gravitational potential. Learning objectives. 13.4.1 Define gravitational potential as a point as the work done per unit mass in bringing a small test mass from infinity to the point. 13.4.2 Use. Theta is equals to negative Gm upon r for the gravitational potential in the field due to a point mass. 13.4.3. Understand how the concept of gravitational potential leads to the gravitational potential energy of two masses and use EP is equals to negative G mm upon R. Temperature, ideal gases, and thermodynamics. Key concepts. 14.1. Thermal equilibrium. Learning objectives. 14.1.1. Understand that thermal energy is transferred from a region of higher temperature to a region of lower temperature. 14.1.2. Understand that regions of equal temperature are in thermal equilibrium. Key concept. 14.2. Temperature scales. Learning objectives. 14.2.1. Understand that a physical property that varies with temperature may be used for the measurement of temperature and state examples of such properties. 14.2.2. Understand that the scale of thermodynamic temperature does not depend on the property of any particular substance. 14.2.3. Convert temperatures between Kelvin and degrees Celsius and recall that T, Kelvin, is equals to theta degrees Celsius plus 273.15. 14.24. Understand that the lowest possible temperature is 0 Kelvin on the thermodynamic temperature scale, and that this is known as absolute zero. Key concept. 14.3. Specific heat capacity and specific latent heat. Learning objectives. 14.3.1. Define and use specific heat capacity. 14.3.2. Define and use specific latent heat and distinguish between specific latent heat of fusion and specific latent heat of vaporization. Key concepts. 15.1. The mole. Learning objectives. 15.1.1. Understand that the amount of substance is an SI-based quantity with the base unit mole. 15.1.2. Use molar quantities where 1 mole of any substance is the amount containing a number of particles of that substance equal to the Avogadro constant Na. Key concept. 15.2. Equation of state. Learning objectives. 15.2.1. Understand that a gas obeying PV is directly proportional to T, where T is the thermodynamic temperature, is known as an ideal gas. 15.2.2. Recall and use the equation of state for an ideal gas expressed as PV is equals to nRT, where N is the amount of substance, number of moles, and PV is equals to nKT, where N is the number of molecules. 15.2.3. Recall that the Boltzmann constant K is given by K is equals to R divided by Na. Key concept. Kinetic theory of gases. Learning objectives. 15.3.1. State the base assumptions of the kinetic theory of gases. 15.3.2. Explain how molecular movement causes the pressure exerted by a gas and derive and use the relationship PV is equals to 1 upon 3 nm(c) squared, where c squared is the mean square speed. 15.3.3. Understand that the root mean square speed, CRMS, is given by c squared. 15.3.4. Compare PV is equals to 1 upon 3 nmc squared with PV is equals to nKT to deduce that the average translational kinetic energy of a molecule is 3 upon 2 kT. Key concepts. 16.1. Learning objectives. 16.1.1. Understand that internal energy is determined by the state of the system and that it can be expressed as the sum of a random distribution of kinetic and potential energies associated with the molecules of a system. 16.1.2. Relate a rise in temperature of an object to an increase in its internal energy. Key concept. The first law of thermodynamics. Learning objectives. 16.2.1. Recall and use W is equals to PV for the work done and when the volume of a gas changes at a constant pressure, and understand the difference between the work done by the gas and the work done on the gas. 16.2.2. Recall and use the first law of thermodynamics. U is equals to Q plus W, expressed in terms of the increase in internal energy, the heating of the system, energy transfer to the system by the heating, and the work done on the system. Key concepts. 17.1. Simple harmonic oscillations. Learning objectives. 17.1.1. Understand and use the terms displacement, amplitude, period, frequency, angular frequency, and phase difference in the context of oscillations, and express the period terms of both frequency and angular frequency. 17.1.2. Understand that simple harmonic motion occurs when acceleration is proportional to the displacement from a fixed point and in the opposite direction. 17.1.3. Use A is equals to negative w squared x and recall and use as a solution to this equation x is equals to x naught sine wt. 17.1.4. Use the equations v is equals to v naught cos wt and v is equals to plus minus w open bracket x naught squared minus x squared close bracket. 17.1.5. Analyze and interpret graphical representations of the variations of displacement, velocity, and acceleration for simple harmonic motion. Key concept. 17.2. Energy in simple harmonic motion. Learning objectives. 17.2.1. Describe the interchange between kinetic and potential energy during simple harmonic motion. 17.2.2. Recall and use E is equals to half mw squared, x naught squared for the total energy of a system undergoing simple harmonic motion. 17. Key concept. 17.3. Damped and forced oscillation resonance. Learning objectives. 17.2.1. Understand that a resistive force acting on an oscillating system causes damping. 17.2.2. Understand and use the terms light, critical, and heavy damping and sketch displacement time graphs illustrating these types of damping. 17.2.3. Understand that resonance involves a maximum amplitude of oscillations and that this occurs when an oscillating system is forced to oscillate at its natural frequency. Electric fields. Key concepts. 18.1. Electric fields and field lines. Learning objectives. 18.1.1. Understand that an electric field is an example of a field of force and define electric field as the force per unit positive charge. 18.1.2. Recall and use F is equals to QE for the force on a charge in an electric field. 18.1.3. Represent an electric field by means of field lines. Key concept. 18.2. Uniform electric fields. Learning objectives. 18.2.1. Recall and use E is equals to V upon D to calculate the field strength of the uniform field between charged parallel plates. 18.2.2. Describe the effect of a uniform electric field on the motion of charged particles. Key concept. 18.3. Electric force between charged points. 18.3.1. Understand that for a point outside a spherical conductor, the charge on the sphere may be considered to be a point charge at its center. 18.3.2. Recall and use Coulomb's law. F is equals to Q1 multiplied by Q2 upon 4 pi epsilon r squared for the force between 2 point charges in free space. Key concept. 18.4. Electric field of a point charge. Learning objectives. 18.4.1. Recall and use E is equals to Q upon 4 pi epsilon naught r squared for the electric field strength due to a point charge in free space. Key concept. Electric potential. Learning objectives. 18.5.1. Define electric potential at a point as the work done per unit positive charge in bringing a small test charge from infinity to the point. 18.5.2. Recall and use the fact that the electric field at the point is equal to the negative of potential gradient at that point. 18.5.3. Use V is equals to Q upon 4 pi epsilon r for the electric potential in a field due to a point charge. 18.5.4. Understand how the concept of electric potential leads to the electrical potential energy of 2 point charges and use EP is equals to QQ upon 4 pi epsilon r. Capacitance. Key concept. 19.1. Capacitors and capacitance. Learning objectives. 19.1.1. Define capacitance as applied to both isolated spherical conductors and to parallel plate capacitors. 19.1.2. Recall and use C is equals to Q upon V. 19.1.3. Derive using C is equals to Q upon V formulae for the combined capacitance of capacitors in series and in parallel. 19.1.4. Use the capacitance formula for capacitors in series and in parallel. Key concept. 19.2. Energy stored in a capacitor. Learning objectives. 19.2.1. Determine the electric potential energy stored in a capacitor from the area under the potential charge graph. 19.2.2. Recall and use W is equals to half QV is equals to half CV squared. Key concept. 19.3. Discharging a capacitor. Learning objectives. 19.3.1. Analyze graphs of the variation with time of potential difference, charge, and a current for a capacitor discharge through a resistor. 19.3.2. Recall and use T is equals to RC for the time constant of a capacitor discharging through a resistor. 19.3.3. Use equations of the form x is equals to x naught e to the power negative t upon RC, where x could represent current, charge, or potential difference for a capacitor discharging through a resistor. 15. Magnetic field and alternating currents. Key concept. 20.1. Concept of a magnetic field. 20.1.1. Understand that a magnetic field is an example of a force produced either by moving charges or by permanent magnets. 20.1.2. Represent a magnetic field by field lines. 20.4. Key concept. Magnetic fields due to currents. Learning objectives. 20.4.1. Sketch magnetic field patterns due to the currents in a long straight wire, a flat circular coil, and a long solenoid. 20.4.2. Understand that the magnetic field due to the current in a solenoid is increased by a ferrous core. 20.4.3. Explain the origin of the forces between current-carrying conductors and determine the direction of the force. Key concept. 20.2. Force on a current-carrying conductor. Learning objectives. 20.2.1. Understand that a force might act on a current-carrying conductor placed in a magnetic field. 20.2.2. Recall and use the equation F is equals to BIL sine theta with directions as interpreted by Fleming's left-hand rule. 20.2.3. Define magnetic flux density as the force acting per unit current per length on a wire placed at right angles to the magnetic field. Key concept. 20.3. Force on a moving charge. Learning objectives. 20.3.1. Determine the direction of the force on a charge moving in a magnetic field. 20.3.2. Recall and use F is equals to BQV sine theta. 20.3.3. Understand that the origin of the Hall voltage and derive and use the expression VH is equals to BI upon NTQ, where T is equals to thickness. 20.3.4. Understand the use of a Hall probe to measure magnetic flux density. 20.3.5. Describe the motion of a charged particle moving in a uniform magnetic field perpendicular to the direction of the motion of the particle. 20.3.6. Explain how electric and magnetic fields can be used in velocity selection. 20.5. Key concept. Electromagnetic induction. 20.5.1. Learning objectives. Define magnetic flux as the product of magnetic flux density and the cross-sectional area perpendicular to the direction of the magnetic flux density. 20.5.2. Recall and use theta is equals to VA. 20.5.3. Understand and use the concept of magnetic flux linkage. 20.5.4. Understand and explain experiments that demonstrate that a charging magnetic flux can induce an EMF in a circuit, and that the induced EMF is in such a direction as to oppose the charge producing it. The factors affecting the magnitude induced EMF. 20.5.5. Recall and use Faraday's and Lenz's law of electromagnetic induction. Key concepts. 21.1. Characteristics of alternating currents. 21.2. Rectification and smoothing. Key learning objectives. 21.1.1. Understand and use the terms period, frequency, and peak value as applied to an alternating current or voltage. 21.1.2. Use equations of the form x is equals to x naught Wt representing a sinusoidal alternating current or voltage. 21.1.3. Recall and use the fact that the mean power in a resistive load is half the maximum power for a sinusoidal alternating current. 21.1.4. Distinguish between root mean square and peak values and recall and use I RMS is equals to I naught upon square root of 2 and V RMS is equals to V naught upon square root of 2 for a sinusoidal alternating current. 21.2.1. Distinguish graphically between half-wave and full-wave rectification. 21.2.2. Explain the use of a single diode for the half-wave rectification of an alternating current. 21.2.3. Explain the use of 4 diodes, bridge rectifier, for a full-wave rectification of an alternating current. 21.2.4. Analyze the effect of a single capacitor in soothing, including the effect of values of capacitance and the load resistance. Quantum physics. Key concepts. 21.1. Energy and momentum of a photon. 21.1.1. Learning objectives. Understand that electromagnetic radiation has a particulate nature. 21.1.2. Understand that a photon is a quantum of electromagnetic energy. 21.1.3. Recall and use E is equals to HF. 21.1.4. Use the electron volt EV as a unit of energy. 22.1.5. Understand that a photon has momentum and that its momentum is given by P is equals to E upon C. Key concept. 22.2. Photoelectric effect. Learning objectives. 22.2.1. Understand that photoelectrons may be emitted from a metal surface when it is illuminated by electromagnetic radiation. 22.2.2. Understand and use the terms threshold frequency and threshold wavelength. 22.2.3. Explain photoelectric emission in terms of photon energy and work function energy. 22.2.4. Recall and use HF is equals to theta plus half mv max squared. 22.2.5. Explain why the maximum kinetic energy of photoelectrons is independent of intensity, whereas the photoelectric current is proportional to intensity. Key concept. 22.3. Wave-particle duality. Learning object. 22.3.1. Understand that the photoelectric effect provides evidence for a particulate nature of electromagnetic radiation, while phenomena such as interference and diffraction provide evidence for a wave nature. 22.3.2. Describe and interpret quantitatively the evidence provided by electron diffraction for the wave nature of the particles. 22.3.3. Understand the de Broglie wavelength as the wavelength associated with a moving particle. 22.3.4. Recall and use lambda is equals to h upon p. Key concept. 22.4. Energy levels in atoms and line spectra. Learning objectives. 22.4.1. Understand that there are discrete electron energy levels in associated atoms. 22.4.2. Understand the appearance and formation of emission and absorption line spectra. 22.4.3. Recall and use HF as equals to E1 minus E2. Number 17. Particle physics and nuclear physics. Key concept. 11.1. Atoms, nuclei, and radiation. Learning objectives. 11.1.1. Infer from the results of the alpha particle scattering experiment the existence and small size of a nucleus. 11.1.2. Describe the simple model for the nuclear atom to include protons, neutrons, and orbital electrons. 11.1.3. Distinguish between nucleon number and proton number. 11.1.4. Understand that isotopes are forms of the same element with different numbers of neutrons in their nuclei. 11.1.5. Understand and use the notation x squared a below z for the representation of nuclides. 11.1.6. Understand that the nucleon number and charge are conserved in nuclear processes. 11.1.7. Describe the composition, mass, and charge of alpha, beta, and gamma radiations. 11.1.8. Understand that an antiparticle has the same mass but opposite charge to the corresponding particle, and that a positron is the antiparticle of an electron. 11.1.9. State that electron antineutrinos are produced during beta decay, and electrons, which are neutrinos, are produced during beta positive decay. 11.1.10. Understand that alpha particles have discrete energies, but that beta particles have a continuous range of energies because antineutrinos are emitted in beta decays. 11.1.11. Represent alpha and beta decay by a radioactive decay equation in the form uranium is equals to Th plus alpha. 11.1.12. Use the unified atomic mass unit U as a unit of mass. Key concept. 23.2. Radioactive decay. Learning objectives. 23.2.1. Understand that fluctuations in count rate provide evidence for the random nature of radioactive decay. 23.2.2. Understand that radioactive decay is both spontaneous and random. 23.2.3. Define activity and decay constant and recall and use A is equals to lambda n. 23.2.4. Define half-life. 23.2.5. Use lambda is equals to 0.693 upon T half, which is half-life. 23.2.6. Understand the exponential nature of radioactive decay and sketch and use the relationship x is equals to x naught e to the power negative lambda t, where x could represent activity, number of undecayed nuclei, or received count rate. Key concept. Fundamental particles. Learning objectives. 11.2.1. Understand that quark is a fundamental particle and that there are 6 flavors or types of quarks: up, down, strange, charm, top, and bottom. 11.2.2. Recall and use the charge of each flavor of quark and understand that its respective antiquark has the opposite charge. 11.2.3. Understand that protons and neutrons are not fundamental particles and describe protons and neutrons in terms of their quark composition. 11.2.4. Understand that a hadron may be either a baryon consisting of 3 quarks or a meson consisting of 1 quark and 1 antiquark. 11.2.5. Describe changes to a quark composition that take place during beta and beta positive decay. 11.2.6. Recall that electrons and neutrinos are fundamental particles called leptons. Key concept. 23.1. Mass defect and nuclear binding energy. 23.1.1. Understand the equivalence between energy and mass as represented by E is equals to mc squared and use this equation. 23.1.2. Represent simpler nuclear reactions by nuclear equations of the form N plus He gives us O plus H. 23.1.3. Define and use the terms mass defect and binding energy. 23.1.4. Sketch the variation of binding energy per nucleon with nucleon number. 23.1.5. Explain what is meant by nuclear fusion and nuclear fission. 23.1.6. Explain the relevance of binding energy per nucleon to nuclear reactions including nuclear fusion and nuclear fission. 23.1.7. Calculate the energy released in nuclear reactions using E is equals to c squared m. Medical physics. Key concepts. Production and use of ultrasound. 24.1.1. Understand that a piezoelectric crystal changes shape when a potential difference is applied across it, and that the crystal generates an EMF when its shape changes. 24.1.2. Understand how ultrasound waves are generated and detected by a piezoelectric transducer. 24.1.3. Understand how the reflection of pulses of ultrasound at boundaries between tissues can be used to obtain diagnostic information about internal structures. 24.1.4. Understand the specific acoustic impedance of a medium as Z is equals to PC, where P is the speed of sound in the medium. 24.1.5. Use IR upon I naught is equals to Z1 minus Z2 squared upon Z1 plus Z1 squared for the intensity reflection coefficient of a boundary between two media. 24.1.6. Recall and use I is equals to I naught e to the power negative mu x for the attenuation of ultrasound in matter. Key concept. 24.2. Production and use of X-rays. Learning objectives. 24.2.1. Explain that X-rays are produced by electron bombardment of a metal target and calculate the minimum wavelength of X-rays produced from the alternating PD. 24.2.2. Understand the use of X-rays in imaging internal body structures, including an understanding of the term contrast in X-ray imaging. 24.2.3. Recall and use I is equals to I naught e to the power negative mu x for the attenuation of X-rays in matter. 24.2.4. Understand that computated tomography CT scanning produces a 3D image of an internal structure by first combining multiple X-ray images taken in the same section from different angles to obtain 3D images of the section, then repeating this process along an axis and combining 2D images of multiple sections. Key concept 24.3. PET scanning. 24.3.1. Understand that a tracer is substance containing radioactive nuclei that can be introduced into the body and then is absorbed by the tissue being studied. 24.3.2. Recall that a tracer that decays by beta decay is used in positron emission tomography. 24.3.3. Understand that annihilation occurs when a particle interacts with its antiparticle and that mass, energy, and momentum are conserved in the process. 24.3.4. Explain that in PET scanning, positrons emitted by the decay of the tracer annihilate when they interact with electrons in the tissue, producing a pair of gamma-ray photons traveling in opposite directions. 24.3.5. Calculate the energy of the gamma-ray photons emitted during the annihilation of an electron-positron pair. 24.3.6. Understand that the gamma-ray photons from an annihilation event travel outside the body and can be detected, and an image of the tracer concentrated in the tissue can be created by processing the arrival times of the gamma-ray photons. Number 19. Astronomy and Cosmology. Key concept 25.1. Standard candles. 25.1.1. Understand the term luminosity as a total power of radiation emitted by a star. 25.1.2. Recall and use the inverse square law for radiant flux intensity F in terms of the luminosity L of the source. F is equals to L upon 4 pi d squared. 25.1.3. Understand that an object of known luminosity is called a standard candle. 25.1.4. Understand the use of standard candles to determine distance to galaxies. Key concept 25.2. Stellar radii. Learning objectives 25.2.1. Recall and use Wien's displacement law. Lambda max is directly proportional to 1 upon T to estimate the peak surface temperature of a star. 25.2.2. Use the Stefan-Boltzmann law. L is equals to 4 pi theta r squared T, the power 4. 25.2.3. Use Wien's displacement law and the Stefan-Boltzmann law to estimate the radius of a star. Key concept 25.3. Hubble's law and the Big Bang theory. 25.3.1. Understand that the lines in the emission spectra from distant objects show an increase in wavelength for the known uses. 25.3.2. Use lambda upon lambda is equals to F upon F is equals to V upon C for the redshift of electromagnetic radiation from a source moving relative to an observer. 25.3.3. Explain why redshift leads to the ideas that the universe is expanding. 25.3.4. Recall and use Hubble's law. V is equals to H naught D and explain how this leads to the Big Bang theory.